SwayamPrabha. Digital India. Educated India.
Welcome back. So let's continue the discussion on turbulent combustion. So far what we have covered, we have looked at the fundamentals like basics of combustion, then thermodynamics, thermochemistry, and then we looked at the characteristics or properties of laminar flames like premix flame or non-premix flame, and then we had discussion on turbulence, where we have seen how turbulent flow behaves and the scaling of the turbulent flows, then the spectra, and then we look at some of the modeling issues like what are the models which are available, how we actually use them. So that's essentially provides you the platform to get into the actually turbulent reacting system, where we will be again looking at the system, different system like turbulent premix system, turbulent non-premix system, and how they interact with the turbulent environment. So it essentially boils down to a, you can think about its turbulence chemistry interaction. So which talks, if you need turbulent flow, you need chemistry. So this in combinedly will give you all sort of turbulent combustion effect. So the flow field is turbulent in nature, that means the underlying fluid mechanics is turbulent. So it will essentially a random chaotic field, and then how that affect the reacting system, at the same time how the reacting system inversely affect the turbulent flow field. So this is the combined effect that we want to look at in this turbulent chemistry interaction. So to give you an overview, this is what you can see. This is where your turbulence is there, and you have reactions and you have applications. So they are sort of intersecting with each other, and so there would be mixing at different scale, and we define things by Reynolds number. So this intersection picture here, it has a plenty of meaning. It tells you lot of things, or it sends you lot of message, which exactly tells you that turbulence affect this affect turbulence, it affects applications also, application affects reaction. So these are all sort of coupled phenomena, and you cannot leave one from the other. Now if you look at the range of application, there is a wide range of application, and this is in this axis, it is the length scale, and this is the Reynolds number. So this is the laminar zone. Then once we start getting into, so this below this line, these are laminar system, but chemical engineering or chemical reactors, oceanography where the dispersion in oceans, environmental science, mechanical engineering, all these, this is the range where you actually see the impact of the large scale turbulence, and if the system is reacting, then the interaction is huge. Now this is another picture of mixing layer, mixing in free shear layer, where the motion of the interface is visualized. you can see there is a structure here and there is a huge difference of the structure, and this is more or like chaotic in nature. And this is happening in a simulation, and simulations depending on your grid or the mesh, this is what you see in grid generated turbulence, and this chaoticness show in your result. But inherently you can observe the flow field to be chaotic. Now again, just to recapitulate the thing, this is what we have been talking again and again. It's a depend on fuel and oxidizer mixing. We categorize them in two categories. One is the premixed, another is the non-premixed. If it is turbulent, so there could be spark ignition engines, gas turbine engines. Non-premixed, if it is turbulent, you have a coal combustion, aircraft, gas turbine, diesel engine, rocket motors. So laminar one already we have done the discussion under laminar cases. So now we want to concentrate on turbulent premixed combustion and turbulent non-premixed combustion, and towards the end we talk about multi-phase system. So that's what. Now this is another picture which is obtained from this experiment, where this is a laboratory scale burner. It's an unconfined flow or the unconfined jet, reacting jet. You can, so this is the methane combustion. So overall reaction you can think about in that methane burning with oxygen producing this. So it's a natural gas, that's why we say. There are major species which are CH4, C2H6, CO2, N2, CO2, H2, and there are minor species which are also involved in the reacting system like CH3, and the importance of minor species has already been discussed in details when we talked about the kinetics and the impact of the kinetics, because these are the species or radicals which are formed and they helps to propagate the reaction. So once we take an OH images, and this is the OH image which shows the reaction zone, and this picture corresponds to the position here, spatial location. This is at the here. Here you can see the jet is coming out, the free shear layer is nicely formed, or the shear layer is formed. Here because under it's something which is distorted, here you can see because of the small scale eddies or because of the turbulence, the reaction zone is distorted or wrinkled, whatever we say. So the impact of the turbulent flow field is clearly visible here. Now again, the OH measurement for a burner, when you look at the reaction zone, this is at a time of 0 millisecond, this is at 1 millisecond, this is at 2 millisecond, and at 3 millisecond. What it shows that at this initial stage you can see it's a nice pattern of the flame, then probably it becomes increase in the temperature, but some point there you can see there is a hole in the flame front, and this is clearly visible here. So these are the situation when the extinction takes place. So this is not global extinction, this is rather local extinction, because you can still see the flame front there that under reaction zone, but this extinction is in local extinction. So that is also a possible situation under turbulent, and that happens because your flow field is turbulent. So under turbulent condition, so when the reaction zone or the flame front is reacting with the small scale eddies, then you can have this kind of local extinction. So capturing or predictions of this kind of local extinction is also quite challenging. So if you put things together in the context of gaseous combustion, so you have if the flow is laminar, then you have complex diffusion properties. If the flow is turbulent, then that immediately gives you wide range of flow, time and length scale. So, that means because of these eddies, you have multiple length and time scale. So, so immediately you can see, one can compare these two situations, laminar to turbulent, and can see the immediate difference in the length and time scale. And obviously, now top of that you need chemistry. So, there are multiple species, they are involved in the reacting system. So, the time scale and length scale would be also wide range of length and time scale. So, that means you have flow time scale, you have kinetics time scale. Then if you have some added situation or added feature which are associated with that phenomena, then you can have radiation, it will have different time and length scale. You have shoot, which will have also different scale, then the coupling with other physics. So, the whole point is that how to handle all this in a computational model, because if one has to look at in a computational field, then one has to look at it. But when you deal with all this, you have to keep one thing in mind, that you cannot actually compromise on the physics. So, your results should be reasonable enough that it should not compromise on the physics. So, this is a simple laminar premix system which we have seen. This is a conical flame. When it comes through these things where fuel and air, lean condition, it is one, you get a conical flame like this, and this is a flame front for simple case. But at the same time, when you look at the situation under turbulent condition, so these are the images from turbulent system. So, you see huge, this is the fuel air mixture coming in, this is the conical, and you can see this structure. This is your flame front, essentially these portions are the flame front, and one of the position is zoomed in and shown here. So, if you look at this flame front compared to the previous picture here, you see a huge difference, and this difference primarily comes because your flow field is turbulent in nature. So, the turbulent flow field has different range of scales, that is large scale, intermediate scale, small scale and smaller scales. So, they are interacting, each of the small and small different eddies of different size, they do interact with the flame front. If I have a flame front like this, then these eddies will interact with that. Some eddies may penetrate, some may not penetrate. So, they will actually have tremendous impact on the flame front, and that is why you get to see this kind of distorted flame front, or rather sometimes you call it wrinkled flame front. So, these are the very unique characteristics of turbulent system. So, what it does at the same time, that because of this interaction process, it actually increases the surface area. Now, thing is that my flame surface can be wrinkled like this because of this eddies interaction. So, once you look at this effective surface area of the flame front, that actually increases. So, it increases the conversion of that, that means more surface area means your volumetric heat release will also increase. So, that will also at the same time disrupt the flame pockets. So, it is one way or other, it is sort of a coupled system. Now, if you want to look at that combined effect, one can put that, okay, this is my turbulent reactive flow, so which contains spectrum of eddies, eddy eddy scales, spectrum of eddy scales. So, when you that halves, so that will allow you to entrainment of reactants by large eddies, which leading to incomplete mixing. So, this will you have different range of scales that will leading to, then you have isosurface stretching, enhancing small scales or small scale mixing, and molecular diffusion, allowing chemical reaction to take place, allowing chemical reaction to occur. So, that essentially, so this can add to also thermo diffusive instabilities. So, that would go to heat release, which will lead to volume expansion and pressure changes. Which modify turbulent flow, which modify turbulent flow. So, that again in turn have the impact on the reacting system. So, if you look at this complete picture, this essentially becomes an kind of closed loop. You may have in fact turbulent reacting system. So, you have a large range of scales because of the eddies. They allow mixing. Large scale eddies react to it differently compared to small scale eddies. Then your isosurface stretches, it helps in small scale mixing and your reaction to take place. Once you have reaction to take place, you have a volumetric heat release. So, due to volumetric heat release, your pressure changes. So, also the local momentum changes. In turn, it changes the local behavior of the turbulent flow. So, it's one hand turbulent affecting the reaction, other hand reaction affecting the turbulent. So, it's an sort of an handshaking. So, and becomes quite complicated because of different scales present there. Now, just some of these description which we have already looked at. So, energy transfer, that is one thing or important phenomena here. From large scale to small scale, the energy transfer takes place, and at the smallest scales, which is Kolmogorov scale, so that is dissipated. Then the scales we can say define the large scale of LT, which is also integral length scale. Then the smallest scale would be eta k, which is Kolmogorov scale, and then velocity fluctuation, standard deviation and velocity fluctuations, which will be u prime, energy dissipation, which is epsilon square by LT, and turbulent Reynolds number, which is defined as RET LT u prime by nu. And all these issues with these things like the scales and all these we have already done detailed discussion during turbulence and all this. This is just to recap, because we are going to use these scales when you talk about this different aspect. Now, one quick thing to go through is the different time scales. Now, typically this is where your physical time scales or the flow time scale that is there, and you can define your integral time scale like Sn LT by u prime, and the Kolmogorov time scale would be nu by epsilon to the power half. So, the ratio of these two time scale would be your RET to the power half, and RET one can define u prime LT by nu. On the other hand, when you look at the chemical time scale, they are quite different. Like if you have a equilibrium chemistry, so they will belong in this. There will be some intermediate time scale, and there is a slow forming species like frozen chemistry or NO formation, they will have this time scale. So, there is a range of scale, especially under chemical time scale, there is a variation, and that variation gives an or opens up a challenge that the flow time scale may behave here and reacting time scale may lie here. How to manage this gap, because there is a gap. So, that is the whole point of discussion, and we will discuss theoretically and also then look at the aspect of the modeling point of view, how we manage to bridge up this gap. So, now if you have a chemical time scale and there is a flow time scale, integral time scale, that ratio called the Damkohler number, which is a non-dimensional number, and the chemical time scale to Kolmogorov, that is the Karlovich number. So, these are the non-dimensional number, that is what going to be used to characterize some of these scales. Now, if you look at these scales, inert flow Smith number is 1, and Kolmogorov scale Smith number would be quite high for liquids. Now, when you look at the premix combustion, the flame thickness is solely determined by the reaction rate and laminar diffusion constant. So, the Karlovich number would be greater than 1, and if Kolmogorov at the Kolmogorov scale, Karlovich number is less than 1. When you go to non-premix system, flame thickness is not solely determined by the reaction rate, it is a laminar diffusion constant, it rather depends on local conditions of the mixing field. So, you can see this how this reaction patterns actually or reaction pattern takes place. This is a natural gas combustion. Already while talking about the thermochemistry, we got an idea about, so that forms some CH3 radical, CH3 to CH2O, CHO, CO, and then it expands. So, overall formation or consumption of species in a premixed stoichiometric flame. So, this goes through multiple branching. So, that is why we have seen the chain initiation reaction, chain propagation reaction, and finally the chain termination, because radicals are formed in between and they actually allow to. This is a situation when you have a rich methane air flame, that means the equivalence ratio is more than 1, and there the intermediate species formations are quite different. but though there would be species formation, because otherwise that without the species formation the reaction cannot propagate. So, that should be there. Now, if we put everything together and when we try to define this reacting system under turbulent condition, so we need some governing equations. So, first thing that we need is the all the transport equations. So, that will have mass, momentum, energy and species. So, these are the set of governing equations or the transport equation that one need to define the system, plus we need transport properties. So, these are also important, transport properties like viscosity, diffusivity, thermal conductivity, like that. Then this can define the flow field. We need kinetics, which is required to represent the reacting system. Then we need thermodynamic equation of state and caloric equation of state. So, that will allow you to calculate properties and all these things. Then if you have radiation, then we need a radiative transfer equation, we need radiative properties. So, this is the set of equation. So, the quickly to get to the transport equation, we can say this is our x, x1, x2, x3 and velocity component would be v1, v2, v3. So, our continuity is del del T of rho del del xj rho bj 0, momentum or the Navier-Stokes for del del T rho vi del del xj of rho vi vj equals to minus del p by del xi tau ij del xj plus rho gi. So, the yk is the species mass transfer equation. So, we can write del del rho yk plus del del xj rho yk vj minus del xj jkj plus wk, and enthalpy equation, that is a specific enthalpy which is a sum of chemical plus thermal. So, which will give me del del T of rho h plus del del xj of rho h vj minus del del xj of qj plus q plus L. So, now this term is a chemical source term, this is the term heat flux, this is heat flux, this is heat source, this is chemical source term. So, these are the set of equations that you need. So, we will stop here today and continue the discussion in the next lecture.